Hey folks, for the video lecture this week, I'm doing something a little bit different, and I hope you like it and that it will help you process through what we need to learn this week. I actually have some stuff pre-written across a bunch of boards, and I'm going to write some stuff in, and I'm going to move the laptop around, so we're going to move around some different boards, and I think this will be a lot easier than me erasing and rewriting a bunch of stuff. So hopefully this works out. I'm kind of excited to try it as we figure out the best way to communicate this information. So we're just going to do a little bit of basic multiple linear regression. You've spent a few weeks now looking at simple linear regression. And what I want to do to help you learn multiple linear regression is simply look at each element that you've seen from simple linear regression and just extend it to what we see in multiple linear regression. And what you'll see is most everything is exactly the same. We just have multiples of it, given the name simple linear regression and multiple linear regression. And to put it in one sentence, multiple linear regression is just linear regression with multiple explanatory variables. That's all there is to it. There's nothing more than that. It's simple linear regression, but now with multiple explanatory variables. So there's no other simpler way to say it than that. So everything that you've learned up to this point will hold the same way in terms of how we interpret coefficients, significance, just different statistics that we've seen. It all holds, but now we actually can start to do a little bit more. And as the challenge sheet, hopefully you saw, you start to think a little bit more about moving beyond one explanatory variable. Maybe there are multiple explanatory variables that we want to look at when we model some response variable. So to demystify and clarify multiple linear regression, let's write in. We'll go line by line and let's write in how multiple linear regression compares to simple linear regression. And I hope this helps you see the jump as you've become more comfortable with simple linear regression, that it's not really that much more difficult to do multiple. There are really only a couple of big implications, which I'll do at the end. But we'll just touch on some things now. So for simple linear regression, our theoretical model is what you've seen a bunch of times before, beta 0, beta 1, x1. That's pretty straightforward. In multiple regression, we can generalize it to say, I'm going to have more than one explanatory variable, so I need to account for that, and I can generalize it to saying beta 1 x1 plus beta 2 x2 plus however many more explanatory variables you need, dot, 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 all the way up to I have this beta k times xk. This just means I'm going to have k explanatory variables. So if k is equal to 3, then I'm going to have 3 explanatory variables. For example, if I was trying to predict the price of a house, if this was price, and we've been getting used to using square feet as our main explanatory variable, maybe I want to put in the number of bedrooms. Maybe I want to put in the number of bathrooms as variables, and I can do that all in one model. So that's really the big jump, is to just add on your extra explanatory variables into your model. And then, of course, the error, like we normally see. So that's really all there is to it. So moving on, our typical error, our residual standard error that I've asked you to look at a number of times in R, this is just a formula. I'm not going to ask you to ever calculate with a formula, but I just want you to see the connection. It's calculated by the sum of squares error, SSE, and divided by n minus 2 square root. you know, whatever formula, but basically this is the same thing, except that doesn't look good. It's the same thing, except we just divide by something a little bit different. The residual standard error depends on how many variables we're using. So instead of, in simple linear regression, dividing by n minus 2 and then taking the square root to get my typical error, now I'm dividing by n minus k minus 1. So in the case of simple linear regression, k is equal to 1. I have one explanatory variable. So then this becomes n minus 1, or n minus 2. So if I have, say, 3 explanatory variables, this becomes n minus 3 minus 1, which is n minus 4. Again, I'm not going to calculate this, but I just want you to see that when we move into multiple regression, a lot of the statistics that we start to calculate to assess whether or not our model is doing a good job depend on how many variables we're using. And that becomes an important issue when we need to decide, do I keep certain variables or do I get rid of certain variables? Changing the variables in your model start to change all these things. So now let's move on to the hypotheses for the slope coefficient. As we've seen before, we just say that my slope coefficient, null hypothesis, is that it's equal to 0. Alternatively, then, it's not equal to 0. Well, the format is basically the same in multiple regression, but now we just generalize it. And what I'd want you to do is write out, if I ask you to write out all hypotheses, is to write out the slope coefficient hypotheses for every variable you use. If I want to write it in one basic expression, then I just say, for the null hypothesis, that beta sub I, so beta of whatever variable I'm looking at, is equal to 0. And obviously, the alternative hypothesis is that this beta, this population slope coefficient, is not equal to 0. So what you could do then naturally is write out some, I'm just going to improvise over here. If you had 2 explanatory variables, then you're going to have, say, 2 null hypotheses of beta 1 equal to 0 and beta 2 equal to 0. And naturally then you'd have alternative hypotheses for each of these slope coefficients. So it's the same thing as simple linear regression, we just have more of them. And the exact same thing is true for how we calculate the t-score on the slope coefficient when we want to evaluate whether or not the slope is statistically significant. Before, we were just taking the explanatory variable slope coefficient, beta 1, and dividing it by its standard error. And that would give us some t-score. And that t-score has a p-value, which we would look up depending on how many degrees of freedom the t-score had. And those degrees of freedom were n minus 2. This is everything that's given to you in the regression table. Again, I just want to make this connection of how this applies to multiple linear regression. So the t-score calculation is the exact same in multiple linear regression, but we just generalize it to say t sub I, to say I'm just doing this for one of my many explanatory variables. And I'm picking the slope coefficient from whatever explanatory variable I'm looking at and dividing it by its standard error. And the only real shift is that when R then gives you a p-value for how significant this t-statistic is to evaluate the slope coefficient. Now it's using a t-statistic with degrees of freedom n minus k minus 1. So the trend we're seeing is that when we add in explanatory variables, everything we've done before still is the same. We just have to do it more times for each explanatory variable. And we can generalize that mathematically with these i's to show it, or you can write it out one step at a time for each variable. And the only big shift is really the degrees of freedom that are used in our calculations for things, because in simple linear regression with only one variable, the degrees of freedom, say when calculating the t-statistic, is always n minus 2. But we need to take into account the extra explanatory variables when we calculate our significance. So in that case, our degrees of freedom on the t-statistic are n minus k minus 1. And just like with the residual standard error up here, if I plug in k equal 1 for my simple linear regression situation, I get n minus 1 minus 1, which is equal to n minus 2, which is exactly what we have over here. So hopefully that makes sense how these things connect to one another. Okay, it may have been a tedious connection of things that are obvious, but this, hopefully you find then that this is pretty obvious or straightforward. That's really good, because multiple linear regression makes it sound like things get really crazy or more complicated. And there are implications for doing multiple linear regression. But in terms of what you are doing and what you are assessing, it's just the same thing as simple linear regression. We just look at a few more statistics to take into account the fact that we are doing more explanatory variables. So let me move on to this next board, which is actually even simpler. Whoop, going a little journey here. Okay, make sure you can see everything okay. So let's fill in the next pieces here. So again, we got simple linear regression over here, and I'm going to fill in some stuff with multiple linear regression over here. It's actually very anticlimactic, and you'll see why in a second. So if you remember that we've been starting with this idea of a response variable is like a big circle with all this variation to it. And if you remember, we thought of this circle as explaining, we've been sort of defining it as sums of squares total. And the sums of squares total represent how much variation I'm seeing in my response variable. And then I can split that up into sums of squares model and sums of squares error. My variation, again, can only go to my model or can go to my error. That's it. I'll just give you a moment to process this. Okay. So given that, how do we actually calculate those sums of squares like we did before? And sums of squares model, sums of squares error, sums of squares total. This is exactly what we had before and what you can see in the book. The formulas for each of these things. Just a quick refresher. The model is the distance from my predictions to my average. The error is the difference between my observations and my predicted values. So that distance. And the total variation that I see is the distance between my observations and their mean. And obviously we square these things and add them all up and do all the math. But in terms of how we calculate all this variation and how much variation is in the model and how much variation is put into the error and how much variation there is total, the calculation is exactly the same in multiple linear regression. So there's nothing new. I know, all my words for a big payoff of nothing. I'm just writing the word same 3 times. But the point is, the way we start to calculate the variation in our model and where it's going, it's the exact same thing in multiple linear regression. All I'm doing is chopping up the y values and the predicted values. That doesn't change in simple linear regression to multiple linear regression. So there's no difference in how these things are calculated, really, or what goes into them. The only thing that changes now in multiple linear regression is that I have more explanatory variables going into my predicted values. So if I have more explanatory variables in my model, then hopefully I'm getting better predicted values and a higher sums of squares model and a lower sums of squares error. That's the ideal. So the big addition that is necessary in multiple linear regression is this idea of testing the significance of the overall model. And we call this the Apt Test. And let me motivate why this is important. And let me go back to our theoretical models for a second. Gosh, I really like using these 3 boards. I just want to say that in the middle of this video. This is much nicer than doing it all on one. So remember when we looked at our theoretical model for simple linear regression, the only thing I needed to assess was whether or not this slope coefficient was significant. So the t-score and the t-statistic hypothesis were great. That's all I needed to do to assess whether or not this model was good. R gave me an F score and an F statistic, which hopefully you saw in the R output video, that the second part of those videos. R gives me an overall model significance with the F score, but it tells me the exact same thing as just evaluating the slope coefficient. So that's all I needed to do. Here's where multiple linear regression becomes more interesting. I have multiple variables here. Each one of these can be significant, statistically, or not significant. So first of all, we have to look at the significance of each of these explanatory variables. But what we can also measure is whether or not the model as a whole is statistically significant. So what I'm saying is you can look at significance at the individual explanatory variable level, and you can look at significance on the overall model level. And so what does this mean for testing the significance of the overall model? In simple linear regression, and as you'll see in multiple linear regression, it's basically the same thing. The overall test of my model is saying that the null hypothesis is that the model does not do better than assuming the mean response variable for every observation. It's saying my model does not significantly predict my outcome better than just saying everything is the mean. The alternative hypothesis is that my model does do better. My model does do better at significantly predicting outcomes, predicted values, than just assuming the mean for every single observation. So the exact same thing is true in multiple linear regression. The wording is the exact same. But there's a little bit of an extra idea loaded in this. And the way the book talks about it, the way it likes to categorize the overall test of significance for the model, is it likes to say that each slope coefficient is equal to 0. Every single one is equal to 0. In the null hypothesis, for testing the overall significance of my model, everything at once, the null hypothesis is that everything's equal to 0. The alternative is that at least one of these is not equal to 0. This is how the book frames it. This is how a lot of people think about it, but I'm going to throw in a little wrench into this interpretation in a moment. The idea is exactly the same across these, and the idea is the same for all models ever. The overall test of significance, what the F statistic is measuring, the null hypothesis is that it does not do better than assuming the mean for everything. The model as a whole does not significantly predict the outcome better than just assuming the mean. And the alternative is, again, that the model does do better. The model can significantly predict the outcome. My observations, its predicted values. So to review, one way the book likes to do this, and the way a lot of people think about it, is to say that my null hypothesis for the F statistic, for the overall model, is that every single one of my slope coefficients is equal to 0. Pardon me, I did not mean to write a beta 0 there. Apologize for that error. I am not going to edit it out. I'm just going to keep going here. But that every single one of my slope coefficients, not the intercept coefficient, my apologies for them, every single one of the slope coefficients is equal to 0. And alternatively, at least one of these slope coefficients is not equal to 0. In terms of how you think about the F test and what it means, I'd rather you just think of it in words and say that the overall model, the null hypothesis is that it does not significantly predict my observations better than just assuming the mean. And the alternative is that the model does do a better job at significantly predicting observations better than the mean. I'd rather you think of it that way, because this is another book error, and I will write it up in an email, but this is not always true. And I'll get back to that when we see this in the future, but these sets of hypotheses are not always true for multiple linear regression. They generally are true, but not under very specific conditions of multicollinearity, which we will talk about in future weeks. Okay. So the main thing I wanted to get out of this board is that we calculate our sums of squares the same, and now we have something meaningful with our F statistic and testing the overall model significance. We may have the case where some of our variables, some of our slope coefficients are insignificant, but the overall model may still be statistically significant. And that's a really important point. So that's an issue that we'll sort of talk about as we run into it. But again, we can evaluate individual predictors, individual explanatory variables with T, or we can evaluate the whole model at once using our F statistic and this idea of the overall model predicting my observations with statistical significance, or not predicting my observations with statistical significance. Okay, that was pretty wordy. Definitely send me questions if that doesn't make sense. But this is just a really neat idea, so I wanted to give it enough time. And the last thing I want to do with this video is move you on to our third board. And straighten the line out and show you one final thing that you've seen perhaps a couple of times in the textbook, but we haven't formally looked at yet. And now I want to formally show it here. Okay, so the book keeps showing this thing called an ANOVA table. And I want to just produce one here for you and talk about where these things come from and why they exist. A little bit better. And all an ANOVA table is a way to show all the different parts of my overall model in one table. And it's just a way to show where everything is when we run a model and run a situation. ANOVA stands for Analysis of Variance. So it's just showing us how our variation in our response variable and the variation described by our model, where that all is laid out. And it's actually a very nice way to look at how these things are arranged. So when I have my modeling situation, I say that I have sources of variation, and this is things that we've seen before. My model can take some variation. My error can take some variation. I'm going to make a line here. And when I put the two together, I get my original total variation. So hopefully this is not new. This is just the same idea that I've got total variation from my response variable, and I can put it into the model or the error. When we talk about how many degrees of freedom each of these things has, we generalize it to say that the model has k degrees of freedom. So that's just the number of my predictors. And the error has n minus k minus 1 degrees of freedom, which we've seen on the other boards. And that my total degrees of freedom is just n minus 1. So degrees of freedom is a weird idea. I'm not going to go through a whole thing about how to define it and what it means. That's more of a stat theory type of thing. But we have degrees of freedom when we use our t-statistics and our f-statistics. And so this is the associated degrees of freedom in each one. It's given to you in R when you run a model, and it gives you a bunch of stuff that comes out. And the sums of squares, this has already been defined before, so I'm just going to write it with the labeling here. In fact, we already saw it defined on the second board over there. So the model sums of squares is SSM. Again, difference between the model and my mean. And with the sums of squares error, difference between my predicted observations, my model, and my actual observations. And I put the two together and I get my sums of squares total, which is the difference between my observations and their mean. So I'm just organizing things that you've already seen before. If I want to take my sums of squares and, in one loose sense of the word, find the mean of those sums of squares, what I do is I take my sums of squares and I divide it by how many degrees of freedom there are for a given source. So I say that the model sums of squares, MSM, is just equal to the sums of squares for the model SSM divided by K. Similarly, mean square error, or MSE, I can just say is the sum of square error divided by n minus k minus 1. And if I want to make a quick connection to things we've seen before, this is equal to the square of the residual standard error. So this mean square error is simply equal to the square of that residual standard error that R gives you. Again, I'm not going to be calculating these things, but I just want to make connections between where things are coming from. And we can also define a mean square total, MST, and just say that it's sums of squares total divided by n minus 1. So I just take the sums of squares column and divide it by the degrees of freedom column. And that gives me a measure of mean squares. There's one last interesting thing we can do with this ANOVA table. And we can actually calculate our F statistic. Remember, our F statistic is that measure of the overall model significance. And I can calculate that by simply taking the mean square of the model, MSM, divided by the mean square of the error, MSE. So all the F statistic is showing me is just a ratio of the model to its error. And to show significance of the model, I want this number to be big. And to connect what it gives you in R, this thing, this F statistic, it has a p-value, just like every other p-value we've seen, and it has degrees of freedom. Because I've got a numerator and a denominator when I calculate my F statistic, we say it has degrees of freedom of k for the numerator and n minus k minus 1 for the denominator. I think that's off the board. I'm so sorry. So when you are given an F statistic, it's just taking the mean square of the model and dividing it by the mean square of the error. And then it's giving you a p-value based on the degrees of freedom for the thing up top, mean square model, k, and the degrees of freedom for the thing on bottom, mean square error, n minus k minus 1. That's why when you look at your R output and it gives you the F statistic, what it does is then it gives you two different degrees of freedom, a k and an n minus k minus 1. You remember, k is just the number of variables, the number of explanatory variables that we're using. Great. So I think that covers it for just showing a sort of overview now of multiple regression and how it extends from simple linear regression. And you've seen this ANOVA table a few times, and now hopefully you see where each of these parts come from. It's just organizing the information that we've seen before. That's all there is to it. So I'm going to I encourage you to now check out the other video where I just quickly touch on two sort of big extensions with multiple linear regression and some implications. But this hopefully wasn't too crazy for you. As I keep saying, you won't have to calculate any of these things by hand, but now hopefully you at least see where they're coming from and why R is giving you what it's giving you. And hopefully that is quite helpful. So thank you much, I appreciate it.